So, welcome, ladies and gentlemen, to the first hybrid meeting of the INCOSE UK World Interest Group. I'm Bruce Elliott, and I'm Associate Professor of Rail Systems here at the University of Birmingham. And it's my great pleasure to introduce Matt Gibson of Amey Consulting, who's going to talk about discontinuous electrification hybrid vehicles. Presumably will tell us I suspect it's going to be something useful in between. I shall look forward to finding out with you, Matt.
Thank you, Bruce. Right, hi everybody. Thank you very much for coming. It's really appreciated. As Bruce says, I'm Matt Gibson. I'm a Principal Engineering Manager at Amey Consulting, and I'm currently seconded full-time into the Core Value Lines transformation, which you might have guessed it from the name, is a project looking at discontinuous electrification and hybrid vehicles. So, you know, I'm come to talk about what and why, but also share some of the sort of the thoughts and understandings I've got through working on the program. So Bruce, if you could move us on, thank you. So we'll talk a little bit about decarbonising rail. This is one of a series of decarbonisation sustainability events that we're putting on. So we'll talk about why and what discontinuous electrification means in that context. We'll then talk about what is the Core Value Lines transformation and some of the challenges that has as a result of it being a discontinuous electrification program. And then I'll come back to the original question, and as Bruce indicated, try and answer whether it is a panacea or whether it is a Pandora's box. So Bruce, that's the wrong way. Oh, no, it's the right way, sorry. And again, thank you. So why do we need to decarbonise rail? I'm not going to try and address the science behind climate change, but let's just look at the government strategy. The government's got a UK carbon reduction strategy, net zero. Along the way to net zero, we need to achieve a 68% reduction in greenhouse gases by 2030. Carbon is one of those gases. And then, sorry, carbon dioxide is one of those gases. And then we need to achieve net zero carbon emissions by 2050. And as part of the government strategy, they've set out one of their commitments, which is to electrify more railway lines as part of plans to achieve a zero carbon rail network by 2050, with an ambition to also remove all of the diesel-only rolling stock by 2040. It won't surprise many of you that underneath that strategy, there's another one. This one looks specifically at decarbonising transport. And again, you'll see the same commitment carried down into that strategy. Underneath that, I've pulled out the two key ones that really set the context for what we're talking around. First is to deliver an ambitious, sustainable and cost-effective programme of electrification. And the second is to support the development of battery and hydrogen trains and to then use them effectively to help us remove diesel trains. So electrification. In the UK, we have perhaps a bit of a potted history of feast, famine, boom and bust within electrification. We make commitments to electrify and then we scale them back. And this happens in a sort of cyclical manner. And people will be familiar with headlines of rail projects going through enormous costs and program increases. And why is that? So if we could just skip on, Bruce. Thank you. So there's lots of reasons, but one of the main reasons is actually not anything to do directly with putting up wire and putting electricity into the wire. It's around making space for that. Our railways were built significantly a long time ago. Electrification wasn't considered originally when a lot of the railways were built. So the clearances that we need just don't exist in a lot of cases. So as a result, a lot of the money and expenditure comes through civil interventions and that are needed to make space for that electrification. So trying to take that away, or anything we can do around that, is what is often going to affect the feasibility of future electrification schemes. Bruce? Yep. Thank you. So if we have a look at a conventional OLE, for those of you who might be familiar with OCS as a term, either overhead contact system. A conventional system is continuous. It goes from A to B. We break it up with neutral sections, and occasionally we use permanently earthed sections in there. And those permanently earthed sections are used to help us mitigate situations where we have clearance issues and we can't achieve our electrical safety clearances. Those OLE systems are navigated by vehicles capable of electrical traction. Some of those vehicles are bi-mode, have the ability to travel on diesel, but what they don't have the ability to do is quickly and frequently switch between traction modes. And as a result, the vehicles that do come across PEZs permanently earthed sections, I will call them PEZs as we go through it, PEZs coast through those PEZs. And therefore we have a risk that because that vehicle is coasting, if it comes to a stand, it will need recovery or it will need to go through a process of switching traction modes. So that often limits our ability to use PEZs on the network because we need to have a reliable service. When we look at hybrid vehicles, the new hybrid vehicles that are being developed have the ability, very similarly to a hybrid car that you might drive, to switch between electric and battery traction dynamically and whilst it's moving, which opens up a lot of possibilities for how we use those batteries and those hybrid vehicles in transforming railways, particularly with discontinuous electrification. There's a couple of examples on the screen that are just other examples of where it's being used. There's the Class 93 freight loco, which is a tri-mode, so it uses hybrid diesel power and can run on batteries as well as OLE. Is being procured by the Rail Ops Group. So that's going to be interesting. That's a freight loco that can navigate in effect anywhere in the UK where it's cleared structurally. So that's going to be quite interesting and open up some opportunities. And we've got the Class 777, which is a Merseyrail vehicle used on a DC third rail network. And they've used batteries, or they're in the process of using batteries, to extend their routes off the end of their third rail system, because it's not really feasible to invest in third rail in the UK anymore, but they can use batteries to go beyond their third rail, turn around and then return to their third rail network. So let's look at the core value line, shall we, which, as I said, is a whole system transformation. This is what is called the Wales and Borders region. And it's fundamentally, it is was a TOC franchise. And as you can see, it covers most of the routes in and around Wales and connecting into Wales. The franchise was coming to an end towards the end of 2018. And in the run up to that, the Welsh government wanted to have an ability to influence the railways better. So they went to see the DfT. And Bruce, if you could flip to the next slide. What they agreed with the DfT, I assume over a cup of tea, was for the DfT to devolve powers to a new organisation called Transport for Wales, who were then in charge of an investment in the Wales and Borders railways. They then let a joint venture contract, which includes the two commercial entities that you need to run a railway, the railway undertaking, who in this case became the train operating company for the Wales and Borders region, operating services over the entire area, just on the screen, and the infrastructure manager, who they also made a development partner, who do two things. They operate and maintain the core value lines network, which Network Rail transferred ownership to TFW to. And then they are also the development partner for TFW to develop the South Wales Metro. This is the South Wales Metro. And what you'll see, the red lines there are the core value lines. So they are the heart of the South Wales Metro. What is a metro? In this purpose, it's defined as 4 trains an hour. And that is deemed to be the difference between people looking at a timetable and planning their journey, or just turning up for the next train. So 4 trains an hour is the magic number where people will turn up and go. So we are transforming these railways into a turn up and go metro style service. So I've talked a lot about stuff, and not specifically about the core value lines. So let's now look at that. So as I said, this is the heart of the South Wales Metro and is key to unlocking what they want to achieve. The first point and I think it's a really important point, is the core Valley Lines transformation is not an electrification project. The reason it is not an electrification project, because if you look at our key output requirements, they do not mention electrification. We are not tasked with achieving electrification. Fundamentally, we need to deliver 5 key things. Capacity, we need to get 4 trains an hour to create that metro service to the heads of the valleys. There's 4 heads of the valleys: Treherbert, Aberdare, Merthyr and Rhymney. We need to also decrease the journey times associated with that. So we have a 50-minute journey time requirement from the heads of the valleys to Cardiff Central, and we have a 55-minute journey time to Cardiff Bay. In doing that, we need to remove the carbon emissions at the train. So currently they're running diesel stock. Now the solution needs to not use diesel stock. Looking at our stakeholders as part of a bigger accessibility strategy, we need to achieve a consistent platform train interface that is usable by all across the network. That effectively translates to what is often referred to as level boarding, which is a consistent, accessible platform train interface. And finally, not satisfied with the railway that they've already got, TfW have a requirement for the transformation to enable a future on-street extension of a tram-style service. So this is a mainline railway currently. Somehow we need to connect it into a on-street service potentially in the future. We have a fixed infrastructure budget, and we have the ability to get some new trains as part of our new franchise. So altogether, where does that put us? Well, it gives us a really interesting whole system opportunity. We've got our infrastructure, we've got our rolling stock, and we have how we use them, our process and procedure, all within our sphere of influence, our system of interest, if you like. We've got our stakeholders around the edge, but that gives us a lot of levers to pull in different degrees to achieve those outcomes. So how are we going to do it? There's quite a lot of clicking here, Bruce, sorry. So process and procedure. Can we use process and procedure? Can we just change what we do and achieve those outcomes? Well, the short answer is no, we can't. Some of it's pretty self-explanatory. We've got diesel stock. We can't just stop using diesel stock without getting some new trains, so we can't do that. What about electrifying it? Well, you know, I've talked about some of the challenges here. The core Valley Lines were built predominantly and originally to serve the mining industry in South Wales. Electrification was not at the forefront of their mind when they built them. And as a result, surprise, surprise, we can't afford to electrify them. And also, if we do electrify it, we can't stick a 25 kV OLE system onto the streets and start running trains around. So it doesn't tick our extendability box either. What about DMUs? Well, hopefully that's pretty self-explanatory. We can't use diesel. We're supposed to be removing it. So new diesel stock is also not the answer. Hydrogen. Again, some of you will have seen the demonstrator at COP26. It exists, but it isn't ready yet. And again, please, but what about hybrid trains? Unsurprisingly, given the title of this presentation, that's what we went with. So let's have a look at the trains. There's two new fleets being procured for the transformation. One is Stadler Class 398 Metro vehicle. This is a tram train light rail vehicle. It's got its traction power options. It runs off 25 kV overhead line, has an onboard battery system, and as I said, it can dynamically transition between these whilst it's moving. Because it's a tram train vehicle, in a light rail vehicle, it's capable of on-street line of sight operation. It's got passive provision built in for adding DC charging. So if we do take this onto a full on-street running, it means we can add DC charging. So we don't have 25 kV OLE in a street environment. And it's got a mid-height floor with a retractable step. And what that does is allow us to achieve that level boarding requirement. The second of the two new fleets is the Stadler again, Class 756 Flirt. Some of you may be familiar with the Class 231 Flirt. It's in service on Greater Anglia. This is effectively the same structural train with a different traction solution. It is a mainline heavy rail vehicle, so different to the 398. Its traction power it's got even more. So this one is 25 kV overhead line, onboard battery with a diesel range extender, which means we can use this train to go beyond the core Valley Lines as part of the broader South Wales Metro and then come back again. And this train again has got the mid-height floor with a retractable step so that we can cost efficiently achieve level boarding. Right, infrastructure time. So we've got some new trains. What does that mean for our infrastructure? And what can we do with our infrastructure? So we've got a map of the core valley lines there. And just to rattle through briefly, what the use of hybrid trains allows us to do is get around a lot of those structural issues that we have. So there's 115 odd kilometers of rail corridor here, and we're electrifying it, but we're also installing 30 permanently earthed sections, so lengths of railway, sometimes up to 1 kilometer or more long, where the wire has no power in it, it is earthed, and 10 catenary-free sections where there are no wires at all. As part of that, and as part of any electrification development work, as you'd expect, we need a traction power distribution system, so we've got a new high voltage connection. We're undertaking a series of line speed improvements, so that passing loops and so on, so that we can get that capacity to the heads of the valley and the journey times. A new integrated control center with a complete relock recontrol so that we can manage the increase in service. Level boarding works across the network where we need to do that to achieve it, as well as a significant amount of station improvements into new stations. And then finally, we are reclassifying. There's a very small piece of the network, which is this piece here. That is the Bay line. That is being transformed into it is currently a mainline railway, and it is being transformed into a non-mainline line of sight railway. So that provides the access into that future on-street running. So the class 398 will run the services down onto that, transition onto line of sight running as part of the service, and provide that future extendability option. So that's what we're doing. Let's look at why it's not as simple as it may or may not seem. So let's look at an example. So we've got the Treherbert to Cardiff Bay run highlighted here. So they're the two red circled stations. It's a 55-minute journey, it's 38 kilometers. And a driver, as they go through that, and a train, will experience 10 permanently earthed sections, 3 catenary-free sections, 2 neutral sections. They'll call it 20 stations, and they'll go through the mainline line of sight transition. I worked out this morning, actually, that if you take out the dwell time that the train spends in platforms, that's effectively calling it a station just over every 2 minutes. So, you know, we're not at a sort of underground level, but we're not too far away from a sort of, you know, so it is a, you know, this is not a, what's the point? There's a lot going on for the driver in the train here. So let's look at how we manage that. Ooh. Cool. So focusing in on what's new, what's different, how do we navigate this new discontinuous electrification? We've got our permanently earthed sections and our neutral sections. So our train needs to, as it approaches those, open and close its circuit breaker, and it needs to transition onto and off of its battery traction. When it enters or exits a catenary-free section, it's got to do that, and it's also got to raise and lower its pantograph. And we need a solution that works for single directional railway and bi-directional railway. There's a lot of single line running on the CVL, so we need to have a solution that works for trains going in both directions. What are our options? Well, hopefully it's fairly self-explanatory that driver controlled, well, that is an option. It could work, but there's so much going on there. It's pretty unrealistic to expect a driver to manage all of that as well as drive the train over the network. So that's not really an option, and we need to look at automating this. The options, we've got APC magnets. We use those on the network around the country already, predominantly to open and close circuit breakers as we go through neutral sections. They do that fine. Problem we've got here is we've got a lot more scenarios and functions that we need to control. And effectively, we just can't manage that with APC magnets. GPS geofencing, it would work, it could work. The challenge we've got there is accuracy, particularly where we've got twin track running, complex track layouts, stations with multiple platforms. We need a solution that deals with that. The accuracy of GPS and geofencing really isn't sufficient, so it kind of ground to a halt that option. ETCS Eurobelize based solution, absolutely a viable solution. Challenge we've got, the trains we're procuring aren't ETCS enabled, equipped. There is no medium to long term requirement for ETCS really on the core value lines. It isn't really necessary. So when we looked at it from a cost point of view, bearing that in mind, we ended up at the solution we're using, which is an RFID tag solution. There's a picture of the tag there that gets mounted to sleepers in the forefoot. And the train has a, the tag is unpowered, it's passive. The train has a powered, energized reader on it. As the train passes over, that will energize the tag, and the tag will send a message back to the train. So, and the train can then act on that message. So this is effectively the solution we've got, because we can control the messages on there, and we can get different messages to our vehicle. Simple. We've automated it. Problem solved? No. With any railway transformation, we need to understand and ensure that when we put our vehicle and our new infrastructure together, they can achieve the timetable that we want to run. And this is no different. We need to do that on the core value lines. The challenge we've got here is there's a whole lot more information that we need to understand as part of our solution that can affect our ability to meet the timetable. And unsurprisingly, that all stems from the discontinuous electrification and hybridization. So the limits of the OLE, when you put them, overlay them onto the geography of the infrastructure, gradients, stations, their effect on the vehicle state of charge is really important to manage, fundamentally, because if the train comes off the wire, you need to know it's going to be able to make it to the next section of wire so that you can run your service. Simple-ish. We need to then take account of what happens if the vehicle's performance changes whilst it's charging, when it's not charging, when it's running on battery, when it's not running on battery. What happens when those batteries start to age? And what's the impact of all of that battery use on the battery life and fundamentally on the whole life cost of our solution? The batteries really aren't cheap to replace. So it's one of our big risks is managing the impact of changes to our solution on battery life. So we need multiple models to predict our ability for the railway to actually meet the timetable. This is an example of some of the analysis that we've done as part of that people may not have seen previously. This is the curve that you can see there is reflecting the vehicle state of charge. What you can see, there's multiple colors. They look at different ages of batteries. We've got the vehicle, whether it's accelerating, braking, or at a constant speed on the yellow line. What you may or may not be able to see at the bottom is a grey line, which shows where we've got powered or unpowered sections. And what you can see is that where there is a grey line, the state of charge generally goes down because the vehicle is running on battery. The vertical sections that we've got marked there are where there's concern around the thermal impact on batteries, timetable performance, and so on. So this is just some of the analysis and some of the thinking that we've had to do and iterate in conjunction with the whole supply chain to try and manage this problem. And as I said a second ago, we also need to manage this as our solution changes. Large rail delivery projects go through change. It's a given. How you manage that change is the question. This is no different. We've just got some fairly interesting.
We're back.
We're back.
And I have no idea why.
Okay, we're back. Can people hear the microphone? That's working again. That's right. Okay, we're back. So as I was saying, everything I just outlined there is made more complicated by change as part of delivery. So we need to manage all of this by change. If we move the position of our wire relative to our gradients, the analysis we've done previously isn't valid. People who've driven an electric car will realize that performance you get from the batteries in your car is significantly affected by how you drive it and what you drive it on. If you drive up a lot of hills, do a lot of standing starts up hills, your battery state of charge is going to very quickly erode. And it's no different for these trains. So where we position our wire relative to the geography of our network becomes really significant. So we need to iterate our modeling to support design decisions, to support and accommodate multiple system life cycles, because trains and infrastructure are not developed on the same life cycle, to accommodate this, all to ensure that our solution remains valid and we will achieve our output. Okay, so we've got a physical solution that works. How do we use it? Well, we know how to run electrified railways. Yes, we do. Can we just apply it to this? Yes, but it doesn't accommodate all the situations we've now got. I've just got a few of them here. Some of these seem fairly simple, and some of them are, but they all need thinking about and accommodating. What happens if we hold a train in a non-powered section? How does the signaller know they're holding a train in a non-powered section? Can they do it? Needs thinking about. What happens if a train fails to read a beacon and doesn't know it's entering an earth section? Does it matter? How do we identify that? And what about if we've got a service perturbation that we need to recover from? How are we going to prioritize service recovery when we're also worried about not having trains stranded in unpowered sections? So there's a lot of thinking there that just isn't part of our normal day-to-day mainline railway thinking. Some of it can and probably will be standardized over time through industry, but some of it, as I said, because a lot of this is affected by geography, some of this cannot be standardized, and we will always have a more complex railway to manage and more complex decisions needing to be made as part of managing a railway. There's a couple of examples here of some of the things you can do in terms of installing additional infrastructure to protect against that. So signage schemes to inform drivers, and we're also providing shore supplies in some strategic platforms. So if vehicles are held, we can plug them in. They won't charge the vehicles, but they'll at least sustain the level of charge in the vehicle. So it's again, how do we mitigate and protect against that? We know what we're building. We think that works. We know how to use it. How do we deliver it? And how do we manage it? Well, as I said previously, there's two legal entities involved in railways in Europe. We've got the railway undertaking, and we've got the infrastructure manager, and they're required to be commercially independent. But we've got a system that is not independent, interfunctional. And when we apply those two organizations over the top, we create complexities, we create interfaces in our system that just aren't there if you take them away. So as a result, the whole system decisions that I've just talked about become even harder to make and harder to manage because we've got inter-organizational decisions going on. Again, exacerbated by programs and life cycles often not integrated, not supporting decision points. And again, differing commercial interests between the two organizations, which again can affect our ability to make decisions that are best for the system. So I'm going to come on to back now and try and answer this question. I've talked a bit about some of the challenges associated with applying this solution, and I'll now try and address the question of Panacea or Pandora's box. Let's just recap and look at some of the benefits and challenges. So doing this and using discontinuous electrification hybrid vehicles, what it allows us to do, it gives us an option to electrify things that might not have previously been feasible to electrify, meaning we can get those diesel trains off the railway. And we can do that with less civil intervention. As a result, that means there's less carbon embodied in the work we're doing, and the result of the work removes carbon as well. Great. If we look at the carbon reduction principles, build nothing, build less, build clever, and build efficiently. Well, originally we looked at build nothing. Can we do this by just changing process and procedure? No. So we can't really do the build nothing approach, but we can do a lot and tick a lot of boxes in building less by reducing a significant amount of civil interventions as part of this. What are the challenges? Well, it's just more complex. We don't have models to help us manage the optimization of this. We've got multiple life cycles programs that we have to manage this across. And therefore, fundamentally, the outcomes and our ability to achieve those program and whole system output requirements just becomes much harder to predict whether what we're delivering is going to deliver those or not. I keep using the word complex. Why is it important? Well, I'm not going to get into what complex means really, but the more complex the system is, the more unpredictable it is fundamentally. And this unpredictability means that we are just at a greater risk of not achieving our output requirements. So therefore, the complexity that we've created in our system by the additional dependencies between its components drive an increased risk in our system. And therefore, we need to manage that basically, so that we ensure we succeed. I stole a couple of diagrams from the Institute of Civil Engineering's Systems Approach to Infrastructure Delivery paper. And these are two of the principles from it that I thought really outlined this. And they are in, by number, the wrong order, but I think the right order. If we bake systems thinking and risk management into our project, and we design an organization structure that allows us to manage that whole system risk to achieving those outcomes, it will allow us to make better design or delivery decisions about what we're building, so that what we build is shovel worthy and not just shovel ready. I heard somebody the other day say, oh, we were an electrification program, and that we aren't, and that is everything that is perhaps driving this risk. If we think about electrification and we focus on delivering electrification, the risk that we can't run our service in the long term because either we don't have the battery capacity or we ruin the batteries as a result of working them too hard is enormous. So thinking about it as an electrification system is carrying an extraordinarily large amount of risk if you don't focus on managing the system, the overall whole system outputs. So can I answer this question? No, not really, and I'm sure no one really expected me to give you a black and white answer. There will be some railways where this really isn't a panacea and will be a complete waste of time and money. A standard electrification approach would be the best solution. But there's a lot of railways where it really would help. Things that previously have been unfeasible from a cost point of view to electrify, suddenly we have options available to us. So yes, in some instances, it could move towards being a panacea. I think the risk and the trick is trying to make sure that the scales tip to that side and don't tip into being a Pandora's box of problems. I've outlined some of the problems that are associated with this that are new and we need to manage. And fundamentally, a systems thinking approach is key to managing those. Thank you very much.
So I'd like to thank Matt for a presentation that covered what was promised, but I think a great deal more in terms of exploring the way in which systems thinking can really help with railway projects, not just in the Welsh valleys, but all sorts of railway projects, and play its part in getting us out of the enormous climate change hole that we're in. So there's time here for questions, and I'm going to invite questions not just from the people in the room, but also from those who are listening in Zoom. So before I do that, let me see. I should get better at this with practice, I should think. Welcome, Anne. And somewhere on here. And then I need to stop sharing that. So you're on a slightly different camera, Matt. And if it's this one,
right? And
if you could move a little bit, that's fine. Then we invite questions. I think if you've got a question on Zoom, just unmute yourself and speak as if you were in the room. We'll worry if we get a collision. Who would like to ask? Please, go ahead.
My question was, on this particular route, are there like many bridges or many parts of infrastructure that are problematic for overhead electrification? Because because it's a short route, it's like 38 kilometers, did you say, or 58?
The whole core valley line is 115. The one example we looked at was 38. Yes is the short answer. Clues in the name slightly. The Welsh valleys have a lot of valleys, therefore the railways tend to run up laterally, longitudinally up the valleys. And there's a lot of bridges going over the railways. There's a lot of space constraint there, and effectively the reason we're taking this approach is because the scale of the civil intervention and the civil works we'd have had to do to continuously electrify it basically made it completely unviable from a cost point of view. So the number, yes, there's a lot of bridges, and that's why we're using this discontinuous solution.
If I may ask, like how much, like how many multiples cheaper were batteries than these civil work interventions? Because if you think about, like, you need several trains, and each one of these trains needs its own set of batteries. So it's not like you're investing in one battery, you're investing in many train batteries. And
yeah,
how much cheaper was that from the civil infrastructure intervention? Plus,
I haven't got a nice easy answer to it. I think it's the perhaps the lazy answer and the best answer I can give you is it was unaffordable. You know, significantly unaffordable. As with everything, costs change and develop the more you understand it. But it was, yeah, completely unviable and significantly unviable to do it as a continuous solution. It's quite, even if I did give you a very, you know, a cost the other way around, it wouldn't be a rule that you could take and apply to other networks because it just depends on the bridges and the geography of that other network as well. I think the other point is it's not just bridges, canopies and in platforms is a big issue. You saw the number of stations we've got. That again, being able to avoid those canopy reworks again adds to the cost significantly.
If I may ask as well, the battery chemistry is, I would assume it's lithium, but
Lithium titanate.
lithium titanate. So yeah, all of the trains are getting lithium titanate, are they?
Yes.
So it's and did you find in terms of so lithium titanate truly have a much longer lifetime than the normal lithium that are in EVs, but did you find that? But there's well a slightly higher cost. Did the slightly higher initial capital cost, was it compensated by the longer lifetime?
If effectively, yeah, the power and the ability to sort of use the batteries the way we're using them just didn't really work. From, I mean, you need to speak to the battery manufacturer ultimately, but yeah, this is really hybrid vehicles, as I understand it, and I'm sure someone will find an example that doesn't match this. But basically, hybrid rail vehicles are really enabled by lithium titanate, lithium oxide. You could use them, but I think long term the whole life costs rapidly. You just knacker your batteries so quickly.
Thank you. I'll turn it.
Okay, do we have any questions from anyone on Zoom?
Bruce, I have a question.
Please tell us your name, Mike.
It is Mike Morrow, and sitting here in Bristol. I do thank you, Matt. It was very, very interesting in seeing that. What I'm interested in is the kind of the long-term, the ways this can be integrated into the railways in Wales. And is there a plan, a timeline, a type of schedule that they'll follow in building this into the system?
Building the solution I just went through.
Yeah.
Yeah, it's being built. It comes into so the first phase of works will be commissioned and electrified middle of next year, with passenger service starting towards the end of next year, and then it rolls on from there. But within about roughly 2 years, that will all be installed and in service and running. both fleets are starting to arrive in the UK. Or in fact, one's nearly here, but the other one's here. It's at Riddick under trial at the minute, so it's happening.
So when you looked at your watch, I thought you were going to say it comes into service in 23 minutes. Okay, Mike.
That's very good.
Anyone in the room? Gentleman at the back, if you'd tell us your name.
Shahid Iqbal from Atkins. So firstly, very good presentation. I think you covered a lot of different areas as far as this electrification or hybrid use of trains is concerned. The first thing I'm quite pleased about is the fact that the rolling stock is being seen as part of the system. I think one of the things that we've been pointing out as far as Network Rail is concerned, Network Rail see rolling stock as outside the system, just cause a lot of problems. So my question really is about the hybrid nature of the rolling stock that you've been looking at and modeling. When typically you run trains on battery, and the whole cycle of charging and using the drawing power from the battery, its performance levels change as a function of time. Did the modeling go into that level of detail or not?
Yes. So I should say that, as I think I said, the modeling has relied on effectively the entire supply chain to do various parts of it to bring it together. So the modeling was done by the vehicle traction provider, which is ABB, and they are delivering the battery solution. So they did the battery modeling. But what we've had to consider, and one of the challenges we've had to overcome, is we do have the vehicle manages its use of the batteries to try and smooth out the performance, so you don't get battery fade as the battery charge decreases. But it differs between the vehicles. But there are some challenges around how it manages that. So we have had to look at that, and the biggest challenge we've had around that is less around modeling that with respect to battery health and vehicle state of charge, because that's, we've gone to the experts for that. But the biggest challenge was integrating that and a variable train performance and scenarios of variable train performance in the timetable modeling, because RailSys traditionally has a vehicle performance curve, and we might need to consider various vehicle performance curves. And some of the conversations and some of the challenges we've had is we have an ability on the rolling stock to potentially, through the control software, use the batteries differently, which gives us different performance curves, and we need to make a decision fundamentally about whether we want to change or stick or change based on long-term forecasts, effectively, in terms of how we use that vehicle. We could have Ferrari performance, but it will very quickly run out of battery, or we can have a more sedate performance, but it will do much more with the batteries, and how we balance that, and whether we want the ability to do a bit of fast and then go back, are some of the options available and are possible with the way these batteries are used. As I said, the challenge is, how do you integrate that with timetable modeling, and effectively you end up having to map vehicle performance curves to geography, and at the minute it really is a bit of a fudge. And as I said, we don't have, as far as I'm aware, in industry, an integrated model that allows us to deal with that. It's something that, it would be a really interesting project to look at, is can we develop an integrated model for this?
Okay, thank you. And the other question, quick question, was about safe by design principles. Now, clearly, one of the concerns that someone like me would have is that the trains at a particular location, it should be panned up when it's panned down, or the time assumed has not really been been correctly verified. Has that been assessed as far as kind of hazards and safety principles are concerned? And based on that, has there been any change in the way that you guys have been designing the processes?
I mean, yes, it has been. Has significantly has been. In fact, we have the people here who helped us with the hazard assessment. So yes. All of the if I sort of particularly focus on the pan up, pan down, because that's fundamentally where the people might disagree where the big risk sits, and the big risk is fundamentally the pantograph hitting something, being up when it shouldn't be up, and how do we control that? Effectively, the system is designed so that the automation is set back from the end of the wire, and then the transition off the end of the wire is designed to allow the pantograph to reach a maximum height and trigger effectively redundancy and a backup system that would automatically lower it. So the system is, there are design features in the system that effectively we designed in some mitigation for that. The vehicles are going through, will go through type testing to verify that, and as I said, it will be one of the things we're going to have to deal with at the minute is how do we bring that vehicle on, and how do we do it's not just how do we commission our infrastructure and our vehicles, we've got a whole new control system that we need to commission as part of that. So the integration testing is going to be quite key to prove the design effectively.
Thank you. So, any more questions from anyone here or remotely? If not, once again, Matt, many thanks. We're really